Hey, what's up everyone? Welcome to the 2019 USNCO local exam stoichiometry section. We're going to be doing all the questions, so questions 1 through 6. And let's get started with question 1, which asks, which hydrocarbon is 84.1% carbon by mass? So for all of these answer choices, we're going to have to calculate the percent mass of carbon. So let's start with CH4, which is methane. And remember, the procedure for percent mass is you take the mass of the carbon and then you divide it by the mass of the complete compound. So let's say we have 1 mole of this compound. If we have 1 mole, the carbon is going to take up 12 grams. And in 1 mole, you're going to have 16 grams of the compound. So in this case, our mass percentage is 75%. Let's look at C2H6 because CH4 clearly is not 84.1. So we have C2H6. It's the same process, but in this case, the mass of the carbon is going to be 24 grams. Whoops, I used the wrong one. 24 grams over the mass of the total compound, which is 30 grams. And if you divide that, you're going to get that it's 80% carbon by mass. So it's also not C2H6. Let's look at C4H10. Carbon in this case is going to be 4 times 12, that's 48 grams over 58 grams. That's the molar mass of the compound. And that is about 83%. So by default, it has to be CaH18, but let's just show it. So in this case, the carbon is going to be 12 grams times 8, so 96 grams over the mass of the entire compound. So you have to add 18. That's going to be 114 grams. And that comes out to about 84.1%. So yeah, it's going to be answer choice D. Let's go to question 2. Lithium hydroxide carbonate decomposes when heated to form Li2O, carbon dioxide, and water. How many moles of water are formed when 0.5 mole lithium hydroxide carbonate decomposes? So as always, it helps to write the chemical equation that's happening here. So we have lithium hydroxide carbonate producing Li2O, CO2, and H2O. If you notice though, this equation is not currently balanced. So in order to balance it, let's first balance out the lithiums. So let's add a 2 on this side. And a lot of things are balanced, but the only thing that isn't balanced so far is the carbon on this side. So let's just balance that out and everything looks good. Okay, so what are we asked? We're asked how many moles of water are formed when 0.5 moles of lithium hydroxide carbonate decomposes. Well, lithium hydroxide carbonate and water are in a 2-to-1 ratio. So for every 2 moles of lithium hydroxide carbonate that is decomposed, we're going to have 1 mole of water that's formed. And this is coming from the stoichiometric ratio. So lithium has a 2 in front of it, and water has an implied 1 in front of it. And so we know that 0.5 moles of lithium hydroxide carbonate is decomposed, so all we have to do is solve for x. And once you do, you'll realize that it's going to be 0.25 moles of water that's formed. And that is answer choice A. Let's go to question 3. A vessel contains 66 grams of carbon dioxide and 16 grams of oxygen at a pressure of 10 atmosphere. What is the partial pressure of CO2? For this question, it's really helpful to know a certain relationship called Dalton's law of partial pressure. And it states that the partial pressure of a substance, P1, is equal to the mole fraction of that substance times the total pressure. And we can apply this to the partial pressure of carbon dioxide. So first of all, let's find out the mole fraction of carbon dioxide. And we can do that by finding out how many moles of carbon dioxide we have and how many moles of oxygen we have. So we know that we have 66 grams of CO2. So to turn this into the moles, we divide by molar mass, and our molar mass is 44 grams per 1 mole of CO2. So we end up with 1.5 moles of CO2. Next, we have 16 grams of oxygen, and we multiply that by the molar mass, which is 32 grams of O2 per 1 mole of O2, and that gives 0.5 moles of O2. So the mole fraction of CO2 is 1.5 moles per the total mole, over the total moles, which is 2 moles. 1.5 plus 0.5 is 2. So our mole fraction here is going to equal 0.75. Let's plug that information to our equation here. So we know our mole fraction is now 0.75, and we're given the total pressure. It's given in the problem statement, and that's 10 atmospheres. And so that comes out to 7.5 atmospheres of pressure. That is the partial pressure of the carbon dioxide. So our answer is C. Let's go to question 4. A first generation automobile airbags were inflated by the decomposition of sodium azide. What mole of sodium azide would be required to inflate a 16-liter airbag to a pressure of 1.20 atmospheres at 17 degrees Celsius? Now, since we're dealing with gas and you're given a lot of information, you're given volume, pressure, and you're also given temperature, this is a clear indicator that you're going to be using the ideal gas law in some way, which is PV and RT. Pressure times volume equals number of moles times the the gas constant times temperature. So which one of these are we given? We're given pressure. Pressure is 1.2 atmospheres. We're given volume, 16 liters. We're not given the number of moles. So N stays a variable. We know R because R is just a constant, 0.08206. And there's units, but I don't want to write them right now. There's like a lot of units, like 4 units or something. And the last bit is the temperature. Remember, the temperature is in Kelvin. So in order to convert from Celsius to Kelvin, you add 273. You can do 273.15, but 273 should get you around the same answer. So 290 Kelvin. And we can plug that into our equation here. So 290 Kelvin. And once you solve, you realize that N equals 0.807 moles. But what is this figure and why is it important? First of all, this figure represents how many moles of N2 is produced. The reason it's N2 and not any of the other things is because we're dealing with the ideal gas law, and the only gas in this entire equation is the N2 that happens, that's produced by the reaction. Now, the question does not ask for N2. It does not ask for nitrogen. Instead, it asks for sodium azide. So how do you relate the nitrogen to the sodium azide? Well, if you look at the chemical reaction, you're going to be producing 3 moles of nitrogen per every 2 mole of sodium azide that you use up. So if you're producing 0.807 moles of N2, how many moles of sodium azide are you going to need? If you do the math, you'll realize that it's 0.538 moles of sodium azide. But the question does not ask for the moles of it. Instead, it asks for the mass of it. So the way you convert moles to mass is just you multiply by the molar mass. So 0.538 moles times the molar mass, which is 65.02. 65.02 grams per 1 mole. And then if you do the math, it's going to be 34.9 grams. And that is answer choice A. Let's go to question 5. Which of the following combinations will produce a 0.4 molar NaCl solution? Okay, so first of all, you have to realize that in a 0.4 molar NaCl solution, you have a 0.4 molar Na concentration, and you have a 0.4 molar chloride concentration. So which one of these answer choices best represents that we have both of these? So for A, you're starting out with the 500 milliliter solution. You're starting out with 500 mils of a 0.4 molar NaOH solution. So what that means is that you're starting out with a 0.4 molar Na plus solution, but since you're adding another 500 mils of water, that concentration is going to get halved. So you actually end up with 0.2 molar Na plus solution, concentration in your solution. So A cannot be the right answer. Let's look at B. In B, you start out with a 1.2 molar concentration. But since you're adding another 600 mils, that concentration of Na plus is going to become 1/3 of that. So you actually end up with a 0.4 molar Na plus solution. So the Na kind of checks out, but we have to also check the chloride. So you start out with a 0.6 molar chloride concentration, but then you add 300 mils. And so that's the equivalent of multiplying your concentration by 2/3. So you also end up with a 0.4 molar concentration of chloride ions. And that matches up with what we want here. So B is the right answer. You could look through the other answer choices to make sure you did everything right, but for the sake of time, we're just going to assume that we did everything right and we got the right answer. Okay, let's move on to question 6. Which solute, when dissolved in 1 kilogram of water, will give the solution with the highest boiling point? So again, question 6 always ends up being one of those colligative property questions. And since we're dealing with boiling point, you know that you're going to be using the change in the boiling point is going to equal Kb times the molality times the Van Hoff factor. Since we're trying to find the highest boiling point, we're going to be trying to maximize this change in Kb number, this number right here. But certain things are not going to change. First of all, Kb is not going to change. For all of these, we're going to be dissolving it in water, meaning the Kb value is just going to stay constant for all of these solutions. They're always going to be the Kb value of water. The other thing that doesn't change here is going to be your Van Hoff factor. If you look at all your answer choices, these are long organic compounds. And the thing about those is that those are not going to dissolve in water. They're not going to dissociate in water. They are weak electrolytes. Therefore, they're all going to have a Van Hoff factor of 1. So the only thing that can really make a difference based on their boiling points is going to be their molality. Remember, molality is going to equal the moles of solute over the kilogram of solvents. For all of these, the kilogram of solvent is going to stay the same because all of these are being dissolved in just 1 kilogram of water. So what we're really trying to see is which one of these is going to maximize the moles of solute. Remember, to find how many moles are in a substance is going to be the grams of that substance over its molar mass. And since we know that all of these substances are going to have the same grams, it's going to be 50 grams. And we're told that from the answer choices. What we're really trying to see is which one of these answer choices has the lowest molar mass. Because having the lowest molar mass is going to maximize the amount of solute that we have. So which one of these has the lowest molar mass? Let's calculate it. So HOCH2, CH2OH, that is going to have a molar mass of 62 grams. HOCH2COOH is going to have a molar mass of 60 grams. HOCH2CHOH CH2OH. I think I messed that up. But it has a molar mass of 75 grams. And the last one, HCOCHO, has a molar mass of 58 grams. So this one is the one with the least molar mass, therefore it is our solution. And that should kind of make sense. Like all of these are really, really big, and this one's is a lot smaller. So kind of intuitively, it makes sense that this one is going to have the lowest molar mass. Okay, so that was the stoichiometry section of the 2019 USNCO local exam. I hope this helped you, and I hope to see you later. Thank you.